Good morning or good afternoon, everyone. My name is Anay Dongre, and today we'll be taking a deep dive into the fascinating world of quantum computing, exploring its principles, mechanisms, key algorithms, and how it compares to classical computers. Here's a look at what we'll cover. We'll start with an introduction and overview, delve into qubit fundamentals and the core quantum mechanics for superposition and entanglement. Then we'll look at quantum gates, circuits, and the crucial stuff of measurements. We'll touch upon famous quantum algorithms like Shor's, Grover's, and the quantum Fourier transform. We'll compare classical and quantum computing, look at hardware and software landscapes, discuss e- error correction, the current NISQ era, future direction, and finally the challenges and limitations before concluding with references. What exactly is quantum computing? At its core, it's a paradigm that harnesses the principles of quantum mechanics to perform computations. Instead of classical bits, we use qubits, which are capable of superposition, allowing them to present more than just one or a zero. The utilization of quantum phenomena enables an exploration of computational parallelism, leading to potential for exponential speedups for specific, very hard problems that are intractable for even the most powerful classical computers. The fundamental unit of quantum information is the qubit. Its general state can be described as a linear combination of the basis states 0 and 1, represented as phi. The coefficients alpha and beta are complex numbers, and the sum of their squared magnitude must equal 1, representing the total probability. A very useful way to visualize the state of a single qubit is a Bloch sphere, where the different points on the sphere correspond to different superposition defined by an angle the- theta and phi. The axis of the sphere also relate to important quantum operations known as Pauli operators. Two key quantum effects that enable the power of quantum computing are superposition and inference. As we mentioned, the superposition allows a qubit to exist in multiple states simultaneously until a measurement is performed. Inference, on the other hand, is a wave-like property where the probability amplitudes associated with different quantum states can add up or cancel each other out. Quantum algorithms are designed to leverage constructive interference to boost the probability of the correct answer, while destructive interference cancels out incorrect paths. Beyond superposition for individual qubits, entanglement describes incredibly strong non-classical correlation between qubits. When qubits are entangled, their fates are linked. A well-known example are the Bell state, where the five star state shows here, which is an equal superposition of 0, 0 and 1, 1. If we measure one qubit in an entangled pair, you instantly gain information about the state of the other, no matter how far apart they are. This phenomena is crucial for things like quantum teleportation and superdense coding, and underpins many advanced quantum algorithms. Uh, to manipulate qubits and perform computation, we use quantum gates, which are analogous to classical logical gates. Some fundamental gates include the Pauli X, Y, and Z gates, which perform bit flips and phase flips. The Harman edge gate is essential for creating superposition. The control gates, like the control NOT gate, are used to create entanglement between qubits, and the rotation gates allows us to perform arbitrary rotations on the Bloch sphere. These gates are assembled into quantum circuits to implement algorithms. After a quantum computation, we need to extract information. This is done by quantum measurement. Typically, This is a projective measurement in the computational basis, 0 or 1 basis. The outcome is probabilistic based on the squared magnitude of the amplitudes of alpha and beta we saw earlier. A crucial aspect is that measurement collapses the qubit state, destroying its superposition and yielding a definite classical bit, either 0 or 1. The combination of these principles, especially superposition, allows for what's often termed as quantum parallelism. With n qubits, a quantum computer can, in a sense, evaluate a function of two n input states simultaneously. However, getting all two n results out isn't straightforward due to the nature of measurements. The real art in quantum algorithm design is using inference to cleverly extract useful information, often just one specific result or property from the massive parallel exploration, leading to speedups for problems like search and factorization. Where when we compare computational power, we look at complexity classes. Classical efficiently solve problems are often in P. Quantum computer define a class called PBQ, which stands for bounded error quantum polynomial time, while BBQ contains P. It's it's believed to contain a problem outside P, or which are classified hard for classical computers. It's important to note that quantum computers are not expected to solve all hard problems, like general NP complete problems, efficiently. Their advantage lies in specific problem structures, such as factoring. One of the most famous examples of quantum advantage is Shor's algorithm, which provides a method for factoring large integers in polynomial time on a quantum computer. This is this is an exponential speedup over the best known classical factoring algorithms. It involves classical pre-processing, then using a quantum subroutine called quantum phase estimation for order finding, and finally classical post-processing to extract the factors. The implications for current public key cryptography are profound. Another landmark algorithm is Grover's algorithm, which offers a quadratic speedup for unstructured search problems. If you have n items in an unsorted database, classically it takes an average of n by 2 and worst case n checks. Grovers can find the items in roughly root n quantum queries. It works by initializing an equal superposition all over n items, then using an oracle to flip the phase of the target state and the diffusion operator to amplify the amplitude of that mark state. This process is repeated about root n times, and this is the algorithm my project will demonstrate. The quantum Fourier transform is a quantum analog for the classical uh, discrete Fourier transform and is a key component in many quantum algorithms, including Shor's. It efficiently transforms a quantum state uh, representing a number into a superposition of different phase states. The QFT circuit uses Harman gates and control phase rotations and has complexity of O n2 for n qubits, which is exponentially faster than n squared complexity of the classical Fourier transform on a 2n input. A major challenge in building a practical quantum computers is the decoherence, the loss of quantum properties due to interactions with the environment and errors in quantum operations. Quantum error correction aims to combat this. It it involves encoding information from one logical qubit into many physical qubits. Codes like surface codes and stabilizer codes are being developed, achieving fault tolerance where computations are processed reliably despite errors. uh, Requires physical error rates to be below certain error thresholds. There are Several different physical platforms are being explored to build qubits and quantum computers. Some leading candidates include those superconducting qubits used by companies like IBM and Google, trapped ions pursued by IonQ and Honeywell, and so on. A spin qubits in semiconductors and so on. Each platform has its own strength and challenges in terms of qubit quality, connectivity, and scalability. Alongside hardware, a rich software ecosystem is developing to program these quantum devices. Frameworks like Quasite from IBM, Cirq from Google, Forest from Riget, and others uh, have others provide tools for designing quantum circuits, simulating them, and running them on actual quantum hardware or cloud-based simulators. My project uses Quasite. We are currently in the NISQ era, noisy intermediate scale quantum. Devices have a limited number of qubits, intermediate scale, and are prone to noise. In this era, uh, developers are exploring hybrid quantum classical approaches. Ex- Example include the variational quantum eigensolver and the quantum approximation algorithms, which use a quantum computer for a specific task within a larger classical operational loop. Prototypes for classical machine learning and simulations in quantum chemistry and material sciences are active research areas. The, Looking ahead, the major goals include scaling to fault-tolerant quantum computers with robust error correction. There are also focus on integrating quantum computers with classical high-performance computing, to developing more advanced error mitigation techniques like NISQ devices and continuously expanding quantum algorithms. The path to large-scale fault-tolerant quantum computing is still fraught with significant challenges. These include limited qubit coherence times, how long they maintain their quantum states, high error rates in gates and measurements, substantial overhead required for error correction, the sheer engineering and cryogenic complexity for many platforms, and the immense resource requirements to achieve a fault tolerance system. For those interested in further reading, these are some of the foundational texts and key papers in the field which have informed the overview. Now, having covered the broad overview of quantum computing, I like to transition to my project where I have implemented Grover's search algorithm using Quasite. This will give us a practical look at how some of these principles like superposition and inference and interference are used to achieve quantum speedup. So let me switch to my Colab notebook. Alright, now let's dive into the practical implementation of Grover's algorithm with my quantum peekaboo project. I've written this in Python using Quasar, which is IBM's framework for quantum computing. The code is structured to first define our problems, then implement a classical search for comparison, and finally build and simulate quantum search using Grover's algorithm. We'll also be visualizing how the quantum state probabilities change. At the top, we are choosing two qubits, which allows us to search among four items. Marked item binary is equal to 1 0, where we are telling the program that items we are looking for the binary state 1 0. The plot state evolution is equal to true. This flag enables the generation of plots using how probabilities of different states evolve. Next, I've implemented a straightforward classical search function. This search function simply iterates through all possible items from 0 to up to n minus 1, incrementing a checks counter until it finds a marked item string binary. This will give us a classical baseline for comparison. Now the core of the project, the quantum search using Grover's algorithm. I've created a helper function called plot probabilities from state vector. The, this will take the quantum state vector from a simulation at different points and generate a bar chart showing the probabilities of measuring each possible state. This is key for visualizing the algorithm in action. We start by defining a quantum a, a register with number of qubits. One, two, step one, initialize. We apply Hartman gates to all qubits. This puts them into equal superposition of all possible states. We'll use our plotting function to see what this looks like right after this step. Let's see. Uh, Inside step 2, which runs on calculated optimal number of items, just once for 4 items, we build the two main components of Groves. First, the oracle. This this part of the circuit is made to recognize a marked item binary 10 in this case. It doesn't reveal the item, but it applies a phase flip specifically to the state in the superposition. The logic here involves applying X gates to qubits corresponding to zeros in our marked items, then a multi-controlled Z gate or or a simple CZ gate for 2 qubits, and then undoing the X gates. Now for the diffusers, this sequence of Hartman gates, X gates, and multi-controlled Z gates, and more X and Hartman takes the phase flipped state from the oracle and amplifies its probability amplitudes while decreasing the amplitudes of all other gates. This is where the magic of boosting the correct answer happens. After each iteration, the plot state evolution is true. We'll again use our plotting function to see how the probabilities have changed. Finally, after the Grover's iteration, we set up the measurement. We add a classical a register to a circuit and then apply the measurement operations to our qubits. This will collapse the superposition and give us a classical binary outcome. To see the results, we use Quasite simulator for visualizing the state evolution. The probability plots, we configure the simulator with method is equal to state vector to get the exact quantum state at intermediate steps. For the final measurement histogram, we run the simulation multiple shots to get statistics on which state is measured most often. This mimics how a real quantum computer would give probabilistic outcomes. The code also includes section to draw quantum circuit and plot the final histogram of the measurement counts. Okay, so that's a walkthrough of how the code is structured to implement both classical search and Grover's quantum search, including the visualization steps. Now now we'll see the output of the code. Alright, here's the output from the quantum peekaboo run. First, the classical search found our marked item 10 in 3 checks, as expected for this case. Our first probability plot after the initial Hardmans would show that if possible, all states would have a same probability of 25% each. This confirms the superposition. Then the crucial plot after just one Grover iteration. This one shows the probability of a target state of 10 jumping to 100%, while others are dropping to 0. This visually confirms the amplitude amplifications successfully pinpointed on a marked item. The generator's circuit diagram visually lays out the quantum gates we applied, the Hardmans, the oracles, the diffusers, and the final measurements. And for our final measurements, simulating 2048 runs, we see that 100% of the time the outcome is 10. The algorithm confirms the perfect success rate for ideal simulation. So, in conclusion, while the classical computer took three steps, our quantum algorithm effectively found the item in one quantum query unit. The real power as the output reiterates is the big O of root n scaling of Grover's compared to big O of n for classical search, offering a significant speed up for large data sets. This project, through its code and visual outputs, clearly demonstrates the fundamental quantum advantage. And that wraps up the project demonstration. Thank you.